Finding a least squares solution would be extremely tedious if we were to actually use the projection formula. We are doing an orthogonal projection. That's what's going on in the background here. But consider the steps you would have to go through if you wanted to do this directly. If you wanted to find the orthogonal projection and then solve this equation. Well, first, you need to find a basis of the column space of A. Finding a spanning set is trivial, but we need a basis. So we need to perform some Gauss-Jordan elimination to get that. 2, we only know how to do this orthogonal projection if we have an orthogonal basis. So once we have the basis, we need to perform the Gram-Schmidt algorithm to get an orthogonal basis. Only then can we do the orthogonal projection. And then finally, we can solve that equation. That's too many steps to be really convenient. Fortunately, we have a method of doing this that bypasses these steps using something called the normal equations. So let's introduce the normal equations. Let's let B hat be the projection onto the column space of B. We're not actually going to find B hat. We'll just define it this way. Then let's let A times X equal B hat. B hat is in the column space. So some vector X definitely exists, such that this equation is satisfied. Now, B minus B hat is orthogonal to the column space of A. So here's the column space, here's B, here's B hat, there's B minus B hat. It's orthogonal by the definition of an orthogonal vector. So let's let A be written as a bunch of column vectors sitting side by side. If this is orthogonal to the column space, it's certainly orthogonal to these vectors. They're all in the column space. So A sub j dot b minus b hat equals 0 for all of these columns. Okay, let me just move upwards to get a little space to work with. This statement is the same as saying that AJ transpose times B minus B hat equals 0. That's the definition of the dot product. This in turn tells us that A transpose times B minus B hat equals the 0 vector. Why is this true? So here is A transpose. Its columns, its rows are the transposes of these columns. You take this matrix, you transpose it, the columns turn into the rows. So we've got this matrix times this vector. So you know the rule for matrix multiplication. Where, for example, to do this product, you'd multiply these elements, and then you'd multiply these elements, and then you'd add them together. And the same down here, you'd multiply these elements, and multiply these elements, and add them together. Well, that is exactly this dot product. So this dot product is always equal to 0. So this is equal to 0. Let's work with this a little, and we're about out of space. So let's start a new page. So we've got this. Way back here, we said that this has a solution. There's an x such that ax equals b hat. Let's take that and let's make the replacement. Ax equals b hat. And this is all equal to 0. Distributing out, gives you this. And from that, if we just take this over here, however, let me switch the sides we have these written on. This is the normal equation. And to do, or to find least squares solutions, you solve the normal equation.